So what is unique about the spatial perspective? So if you think about data, there's all kinds of different data. There's all kinds of different ways you can organize data. But spatial data, again, sometimes we use spatial and sometimes we use geographic. So spatial or geographic data are things that are measured in a particular location. So that means that while you might use other kinds of indexing systems for other kinds of data, for spatial data, we use location as the universal thing that indexes all the data. So that means that we can look at, if you just think about where you're sitting right now, we could have data for that location that has to do with the geology, the soils, the vegetation, the built environment, the building that you're in, perhaps the chair that you're sitting on. Then it might have some data about you, your health, or your height, or a variety of things. But if you almost imagine that you just drill through that location, there's all these layers of data. And what's happening at that location, how happy you're feeling, how well you are, how much fresh air you have, all those things, they all relate to that location. And so that is really the cool thing about spatial perspectives, GIS, spatial data science, is it really allows you to look at things in the context of where something is. And when you can understand where something is, you actually have a lot of power to look at interdisciplinary things, so multiple kinds of data, as well as to be thoughtful about how that interacts with things around it. So this is a classic view of GIS where you have multiple, what we sometimes call layers of data. So we might have data on streets, data on buildings, vegetation data, and all of that can be integrated into something that allows you to understand the world around you in a more complex way. So one of the ways you can think about whether or not the data that you're interested in is spatial is it is always a collection of data taken at a particular location. And if you can map the data, then it's spatial. So this is like a growing amount of mapping data because we create it from satellites, we create it from a variety of things on the internet, we can create it from our phones. So we have a lot of apps that are working in the background collecting data. That data gets packaged up and sold. So there's a lot of sources of spatial data. It could be data on everything from where individual trees are. It could be data on something to do with a variety of different kinds of soils. So this is, national level data. Could be data on census districts. We use census data a lot in GIS science. So you'll get exposed to a lot of different kinds of data. But really, the key thing is spatial data, geographic data have location information. One of the things that makes them interesting is they often have other things associated with them. So you could have points that have locations, so X, Y coordinates, lat longs, UTMs, but you also often have associated with that data a bunch of other variables. So if these are locations of schools that you can put on the map, these points also have names and they also have school types and a variety of other things. If you had a map of trees, the XY coordinate is important, but the species, the health, the height of that tree could also be important. In city planning, we can have a lot of information about where things are located. Things like hospital locations can be important. This used to be kind of a foreign concept, but now that you use Google Maps, you can kind of imagine, like if you want to look up where is the nearest grocery store, you also want to know, what hours is it open, and a variety of other things. So GIS is really dealing with the fact that we need some way of storing that in a digital way. So when you think about any kind of data is really a model or a representation of the world around us. And so you need to put that in a computer somehow. And well, we're used to working with it because we navigate and look stuff up on our phones. Early on in GIS, a lot of thought went into how are we going to take these models or this data that represents the world and stick it into a computer. I think this image kind of gets at the idea of a model quite nicely. So we have the world, we have what's real, And we take components of it and we stick it into these layers of data that we put together to try and get a good representation of the world. So this bottom slice here that says real world, it's really trying to represent reality. But even from this diagram, you can see, it is just a representation of reality that incorporates a bunch of different things. So how you decide to put your data into the computer or the GIS, it has a lot of impact downstream in terms of how you conceptualize the problem you're working on, how you analyze data, and also how you interpret and analyze results. So here's a diagram. Oh, that's showing up. There's like a header here. Okay, so here's a diagram that kind of shows the things that we're going to go through today. So there's two layers that we're going to think about this on. One is on data models. So this is sort of like conceptually, how do you think about the data that you put into your computer? And then the representations, which are kind of like practically, what does that look like? So there is a fifth thing down here, which we're not going to talk about today, but I'll be super impressed if someone who watches this video can figure out what that one should be or was before I hit it, because we're not going to go into that much detail today. Okay, but let's first start talking about data models. So this is kind of the conceptual component. And data models are mechanisms for establishing relationships between scientific theory and the world, or between how we want to represent or model things. Model could be another word for scientific theory and the world. And there's two kinds of things that we use. So one is where we consider things objects, and another is where we consider things field. And I'll define both those. But if you've ever heard of sort of object-oriented programming, the object-oriented component means that it's thinking about data in the object way that I'm going to talk about. So in the object model, space is conceptualized as a collection of objects in a container. So it means that it assumes, or it represents the world as though everything kind of has distinct boundaries. So some things that are really smart to represent this way tend to be things like buildings. They have like boundaries that you can draw. And so those will often be thought of as an object in your database. And you can describe, the location of the exterior walls. That'll be the spatial component of the data. And then you could have attributes like, this is a medical building. This is where the geography department is housed. So here's an example of what it could look like. Points on a map that mark down, in this case, this is oil wells. That's a good example of an object model, because you could imagine, each of those wells has a footprint. Depending on how zoomed in your map is, the scale of your map, you could just represent it as a point, or you could draw a boundary around it. In this case, each oil well has a spatial location, and then it also has some attribute information. Who owns it? What does it produce? When was it? When should it be decommissioned if you live in Santa Barbara? Land parcels are another good example of things that are often represented with an object model. So here we can see, these kind of land parcel data are used a lot in planning. All cities have them because they're often used for tax assessment. And each of these parcels has a property boundary that can be easily represented as an object. Another good example is light poles. So they have like very specific locations. Now, the field model is when something doesn't have good boundaries. And like the best example I can think of is temperature. So if you were going to map temperature, you can't draw a boundary really around temperature. It's just everywhere. And so in these cases, we consider phenomenon to be best represented by a field model. That means like a kind of a continuous field. And one way I like to encourage students to think about it is if you had a map in front of you and you closed your eyes and you put a pencil down, if you could open your eyes and every single location would have a value, then that means you're dealing with a field model. So if we had a map of temperature you could put your pencil down. Every single location has a temperature. So that's a good thing to represent as a field model. Another example might be elevation. Everything has an elevation. But if you were going to go back to your land parcel, if you drop down your pencil, you could end up in the middle of a street, which doesn't have a value, doesn't have a land parcel value. And so that is a phenomenon that's probably better represented as an object. So a little more on field models. Think about soil salinity. Every location on the surface of the earth has a soil salinity. And maybe you can't measure it at every single location, but even if you don't measure it, it exists. And so usually when we represent things as a field model, we have some kind of way of, just like some practical way of breaking up space and then assigning each value a location. And I'll give you a bit more detail about that. But yeah, many things that we think of as physical geography are field models: precipitation, temperature, geochemistry. Okay, so that's conceptual. So conceptually, we have objects and we have fields. But I'm going to talk about 3 ways in which we think about actually the practical representation of objects. So I showed you a few of these, but now let's get into the details. So how do we implement these different things? So if you are thinking about a field model, no, cancel that. If you are thinking about an object model, these are things that are discrete. We use 3 kinds of geometry basically to represent these: points, lines, and areas. So the points are just things that are mapped with an XY coordinate. So this might be the location of a tree, might be the location of a house, it might be people sitting around a fountain, it might be the location of animals. So these are often, it's not always, but often points are best used with individual data. You wouldn't necessarily map like a cluster of people as points, though that there are cases where that occurs, but more often it would be like every point. This is a near infrared image of a forest, and you can see there's streams, and so all those pink things are different trees. So if you made a map where every single one of those was a point, that would be a good example. And the points are kind of considered the simplest form. And then next, and it's slightly more complicated, is when you have a bunch of points that are mapped together to make a line. Sometimes in the case of a line, you have the first and last coordinate are called the nodes, and the line is represented as an arc. So you can, like, imagine if you are digitally drawing a line, what's actually happening is that there's like a bunch of points that are super, super close together effectively that make the line. So lines are considered like slightly more complex, and roads are used a lot. Lines are used a lot for things like roads. You can even have, roads, lines that all connect to each other, what we call networks, but we're not going to worry too much about that. So the first is points, the second is lines. River segments, also an ideal sort of ideally represented as a line. Hiking trails represented as lines. The third kind of object that we map is something to do with areas. So it could be a regular area, or it could be an irregular area. Usually it's like a line where the first and last points are the same, essentially, so that it connects up. It has like, it closes somehow. And areas are used to represent things like forest polygons, lakes, census district, watersheds. Parcel boundaries are an example of areas, usually. There's another thing. Oh yeah, building footprints would also be a good example of something that's typically represented as an area. So when you have objects represented as areas, again, in the example of the land parcel, you could put your pencil down and have a 0 value there. That's important to keep in mind, because we're going to talk about field representation. So these are the things that are continuous. So if you could just do data science in your imagination, you probably wouldn't need to worry about this, because you can imagine a scenario where everything is measurable and you have measured all temperature, but that's not actually how it works. What actually happens is we measure temperature at a bunch of locations, and then we usually use some kind of mathematical function to sort of spread or predict the value at a bunch of unsampled locations, because it's just not practically feasible to measure everything everywhere. And even if you could go to many, many places, like physically, how would you figure out what was the minimum unit of sample? Like conceptually, it's kind of fun to think about how you would avoid having to use these models. And it reminds you that really models are a really important component of representing any kind of data. So in the field representation, we're going to talk about rasters. And rasters just mean that you have tessellated or divided up this space into a bunch of repeating shapes. So I'm just going to show this image. So here, usually the most common raster is this square, but hexagons are increasingly used. Hexagons are actually like super handy because of the way they define spatial proximity. Anyway, that could be for an analysis lecture, but I think if we had really been thinking, we would have designed all of our maps on hexagons, but instead we use squares, which is fine. So we're going to really focus on the squares today. So rather than trying to measure temperature or represent temperature at every single location on the Earth, what we do is we cover the surface of the Earth in a series of grid cells, often squares, and then we calculate a value for each of these. And there's some really nice things about using grids. Like they're super easy to store, and mathematically they work faster. So when you have massive data sets, they compute more quickly. We put into this things like soil moisture, precipitation, geochemical data. So you can see in this case, it looks like smooth. It looks smooth. It almost looks like we just drew areas around different things. But what's actually happening here is that the grid cells are so small that your eye isn't really picking up the edge of the grid cell, and it looks smooth. But this data is still stored as a grid cell, and appropriately so, given that if you put your pencil down and you opened your eyes, there would be a value there. So this is an image actually of forests that up here, you can see these are very recently planted trees, and then these are the mature forests down here. It's an image, but all images are actually stored as rasters, and which is interesting. But then how would we calculate, if we wanted to calculate the average soil moisture, we would, and represent it as a raster, you couldn't do average soil moisture as a vector, because soil moisture cannot be identified as, a unique object. So you put down a grid, and then you might calculate the average soil moisture in each cell, and that might be based on a couple of samples that you take, throughout your grid cell, ideally. When you store that data, one of the ways that you would store it is just like the matrix. So you would call this some kind of matrix storage, where you don't actually reference the spatial location, but you just have, your starting point, kind of one of your corners, and then you know how big each of your raster grid cells is, and then you can just store all the data, making it efficient. And then sometimes we also store it like this, where we say row 1, column 1 equals 5. And then we can give row 1 and column 1 a coordinate, and we can also know how big each of these grid cells are, so that we can do all the mapping that we need to do. Okay, so I'm just going to zip back up here. So I think this is the nuts and bolts. Okay, so just to review then what we've talked about, GIS, we've talked a bit about that. It is how we deal with spatial data. But we really focused in this lecture on thinking about how do we represent spatial data. So sometimes we can think of it as an object. And if we do think of it as an object, then we have to decide, are we going to use points, lines, or areas to represent that data. And then other times it's a field, so it's something that is continuous. And usually we use a raster, and here we've really focused on grid cells that are square, but hexagons would also be something. And then there's something else, mystery down here, which we didn't talk about today. It's just a level more complicated than you need. But if you email me with it, I'll be so impressed. Just gonna go back down to my last slide. Okay, so spatial data are cool, in my opinion, because it really allows you to integrate a lot of different things across space. I always think of like geographic locations. It's a universal indexing system that we have already built for the entire world. So you have a way of organizing your data, which I think is super cool. Because of that, you can integrate a lot of different kinds of data in a GIS. Anything about that location and what's around it can be incorporated. Then again, so we have the two data models, objects and entities. You can think about these as implemented through vectors, which are your points, lines, and areas, or rasters, and we really focused on a lattice or a grid in this case. So hopefully this gives you some insight into the conversations that we're going to have over the next little while. People will do all kinds of things with these data. They'll layer in lots of really cool data sets. They'll find new ways of querying them. They'll do advanced statistical analysis on them. That's my favorite thing, is really the analytics of these data. But most of the work you'll find is often associated with just getting the data organized. So it's good to have that clear in your mind. So thanks, everybody.